In this lesson, I'm going to be doing an example where we're calculating for the pressure. Now, in the lecture, we learned that pressure is a function of depth. Specifically, pressure is equal to the specific weight of the fluid times h, or we could express that as rho g times h. Okay. In this example, what we're interested in is knowing the pressure at point A. We have a given atmospheric pressure of 101.03 kilopascals. We have a layer of motor oil that's 1.5 meters deep. The motor oil has a specific gravity of 0.89, so again, it's 89% the weight of water. We have water itself, so it's specific gravity BB1, and we have 2.5 meters of that. And then at the bottom of everything, we have some olive oil, okay, which is the heaviest of the solutions, right? It has a specific gravity of 1.93 at a depth of 2.9. And again, if we just look at this, this makes conceptual sense, right? We have the heavier fluids at the bottom, right? The heaviest is the oil at 1.93. In the middle, we have water with specific gravity of 1. And then we have a specific gravity of 0.89 for the motor oil. Okay. So again, what we're after is calculating the pressure at point A. Okay. I'm going to start by computing the specific weights of the different fluids, because we're going to need that in our equation, right? When we go back to this equation, basically what we're going to be doing is we're going to be summing up all the individual pressure terms. So the specific weight of the motor oil, and I'm just going to use the subscript MO for motor oil, is going to be the specific gravity term times the water value. Okay, for water, we're going to work in kilonewtons this time. So specific weight of water is either 9,810 newtons per meter cubed or 9.81 kilonewtons per meter cubed. Okay, so for the motor oil, we get a specific weight of 8.7309. I usually don't carry it out that far, but I'm going to just keep the decimal points to that point, to that level, and that would be kilonewtons per meter cubed. Okay. We already know the specific weight of water. That's the 9.81 kilonewtons that we just talked about per meter cubed. And then specific weight of the olive oil, I'll just say O for olive oil, I guess, instead of doing OO. Okay, that would be, let's see, the 1.93 times the 9.81. Okay, and that comes out to be 18.933 kilonewtons per meter cubed. Okay, so now I know the specific weights for all three of these liquids, and our approach will be basically to sum up all these pressure terms. So what we'll be doing is we'll go through and we're going to be summing up all the gammas times h to get the pressure at point A. Okay. So I start at the very top here. So at the very top, I have a pressure of atmospheric pressure. Okay, so we're going to write an equation. We'll say P of A is equal to, let's go with our atmospheric pressure. I'm just going to keep things in terms of generic terms first before we substitute. Okay, so I have my atmospheric pressure. And then I'm going to have the pressure from the motor oil. Okay, the motor oil has a specific weight. Well, I'm going to just keep it in generic terms first. I'm sorry. Gamma motor oil times the 1.5 meters. Okay, then we're going to have this piece here, right, with the water. So we'll have the gamma of the water times the depth of 2.5 meters. Then plus, and then the last piece, we have the gamma of the olive oil, and that has a depth of 2.9. Okay. So if we just start substituting some of these terms in, okay, pressure of atmospheric pressure was 101.03 kilopascals. Okay, we've got gamma of the motor oil, which is 8.7309. I'll carry that through for a little while, times 1.5, plus the gamma of the water, which is 9.81 at a depth of 2.5 meters. And then we have the last term, which is the oil, the olive oil, which had a gamma of 18.933 at a depth of 2.9. Okay, and just kind of spelling this out a little bit just to make sure I didn't make any calculation mistakes. I get, let's see, 101.03 for the first term. Let's see, 8.73 times 1.5 comes out to be 13.10. 9.81 times 2.5 comes out to be 24.53. And then the last term, which is 18.933 times 2.9, comes out to be 54.91. And so our final answer for the pressure comes out to be 193.57 kilopascals. Okay. And again, the atmospheric pressure of that, the component of that was just a little bit over 100. So we essentially have around 92 kilopascals of fluid-related pressure plus the atmospheric pressure of 101 gave us a total pressure of about 193.6 kilopascals. And then with that, that concludes our example.